graph y is equal to the quantity x plus 1, whole thing squared, and then divided by 1 over x squared. Alright, so how do we graph this? We know it's a rational function, so the first thing we have to look at is the domain. Okay, remember we look at the basic graph, and we know that it's a rational function. Look at the critical values, which means we take the first derivative, and then use second derivative test if we want that, or we can use the first derivative test. Sometimes it depends on the function whether it's hard to get its second derivative, but we're still going to need the second derivative anyway because of finding the points of inflection, and then we use the second derivative test for concavity. And then plot those critical points and at any additional point, and I think we're ready to go. So let's go ahead and let's define the domain. Alright, what is the domain? What is the domain of this function? Just because you have a variable in the denominator, that doesn't mean that you will have a vertical asymptote right away, because look, 1 plus x squared will never be 0. So that means the domain is all real numbers. Now, another thing we look at, since it's a rational function, go back to section 2.6 where we talk about asymptotes. You see that the highest degree or power on the numerator is 2, and the highest degree on the denominator is also 2. So whenever you have the same degree in the numerator and the denominator, then you have a horizontal asymptote. Would be the ratio of the coefficient of the leading term, which is here. It's just 1 x squared. You know, when you FOIL that whole thing, you'll have an x squared term. So 1 over coefficient of x squared is 1. So we will anticipate that you have a horizontal asymptote at y equal to 1 and no vertical asymptote. So let's go ahead and look at critical numbers. So let's take the derivative y prime. Alright, so we have a ratio, so always start with the square of the low we go. 1 plus x squared whole thing squared, that's square of the low we go, and then low d high. So let's just take the bottom, and the derivative of the top is 2 times x plus 1, and then I'm going to put 1 here. That way we know that we use chain rule, because if there's a coefficient there other than 1, then you'll forget. Low d high less high d low, so we'll just take the top, which is x plus 1 whole thing squared, and then multiplied by the derivative of the bottom, which is just 2x. Right? So again, we don't do anything with we don't FOIL the denominator, so we just keep it the way it is. Now look at here, we have x plus 1 as a common factor, so pull out x plus 1, and then we also have 2 as a common factor, so 2 times x plus 1, pull it out, and what do we have? We have what's left inside, so we pull out these two things, so we're left with 1 plus x squared, and then minus, we see that this is what? This is an x plus 1 is still left as a factor, and then you've got another x, right? Because you pull out a 2 and you just pulled out one factor of x plus 1, so there's still one more remaining. That's where we got that. And then whole thing divided by whatever was squared. Okay? And then next is just keep going and look at what's on the top. So we take 2 times x plus 1, and that becomes 1 plus x squared, minus, if you distribute the x, we've got x squared, and you distribute the negative, you have minus x, and look what we got here, and square of the bottom. Alright, this gets cancelled out because they're opposite sign, so we're left therefore with 2 times x plus 1 and 1 minus x over the square of the low we go. That's 1 plus x squared, 1 plus x squared. Now when we set this equal to 0, we will see that at x equal to negative 1 and at x equal to 1, we have those critical numbers. So y prime is 0 when x is equal to negative 1 and positive 1. Okay? Because all you do is just set both the numerator to 0. The denominator will never be 0, so there's no 0 in the denominator. So let's check that out. Okay. Now, there's what do we do next? Well, it's either you take the second derivative test or you use the first derivative test. Either way, okay? Now suppose we use the first derivative test just because if we want to avoid taking the derivative again. However, we're going to use it anyway, but let's just say we want to use the first derivative test. Why not? Okay, so let's take -1 and 1. So in here, we're just using this first derivative test because that will give us a local max or min. So these are just your critical numbers, and we don't know yet whether they're local, max, or mins. So we take a test point, and every time I do a test point to distinguish that from these numbers, okay, I encircle it. So -2. Another test point, of course, would be 0. That's a good number to test. And to the right of 1, let's test 2. And take the sign of the first derivative. Okay, so plug this into the first derivative. So y prime at -2, that would be negative times positive. We'll make it negative divided by this is always positive, so y prime would be negative. Right? What about y prime at 0? So that means it's decreasing. And then you have a 0 slope. And then what happens here? Well, we'll see. Next is when x is 0, we plug into the first derivative. That's going to be 0 plus 1, that's positive. 1 minus 0, that's positive. So positive times positive over positive would make the first derivative positive. So you're increasing. So that tells us that at x equal to, okay, I'm just doing that so we would know that it is, it divides our number line, and the same thing here. So we would know which intervals they're increasing and decreasing. So from -infinity to -1, you have the function is decreasing. So we say that you have a local minimum occurring here. And then we'll see. We have again a 0 slope right here. Now what happens is x equal to 1 a local max? That's the question. Well, we'll see if the derivative is negative. So let's go ahead. So here it's positive. So y prime at 2. So you plug 2 in here. That's going to be positive. 1 minus 2 will be negative. So positive times negative divided by positive is negative. So here when we plug in 2, our test point, into the first derivative, we see that the sign is negative. So that concludes that you have a local max occurring at x equal to 1. So far, what have we discovered? When we took the first derivative, we set it equal to 0. We used the first derivative test. Notice that we used the first derivative test. Again, you can use the second derivative test if you want. I just showed you that you can do both ways. Alright, so let's see what's going on now. We found a local min and a local max. Now our next step is to find points of inflection. Okay, let's continue on. So far we found a local minimum at the point -1, 0 and a local max at 1, 2. Okay, what's next? Now we try to find points of inflection. So recall that to get a point of inflection we need to get the second derivative. So let's find y double prime. So if y prime from the previous slide is equal to 2 times the quantity x minus 1 times 1 minus x, if you rearrange this, it'll become 1 plus x times 1 minus x. You'll get a difference between squares. Multiply that by 2, and then so you have 2 minus 2x squared divided by the square of the law. We go. Okay, so we use quotient rule in here. So let's do that. And what is then the second derivative? Square of the law we go. Now, where did I get 4x? 4x is the derivative of the top. So low d high less high d low. So what is what do we have? That's 2 times, let's see, what is the derivative of the bottom? It'll be 2 times 1 plus x squared, and then you take the derivative of the inside by chain rule 2x. So this is now high d low. So low d high less high d low. Alright, so now, and then square of the low we go. Okay, let's just simplify those. So you see that x plus 1, quantity x plus 1, quantity 1 plus x squared is a common factor, so pull that out. And we see what else is a common factor. We see that 4x is a common factor because it's here and it's here as well. In fact, it's the negative 4x that's a common factor. So negative 4x is a common factor and 1 plus x squared. So what's left inside would just be one of the factors of 1 plus x squared. So you get 1 plus x squared plus this remains in here. This was not factored out. And if you rearrange all that, you'll have 1 plus 2 is 3. And then you have x minus x squared minus 2x squared. That gives you 3 minus x squared. So you've got 4x times 3 minus x squared. And then what do? We take the second derivative and set it equal to 0. Now again, the denominator will never be 0, so we just set the numerator equal to 0. So what do we get? Okay, you have negative 4x 0, which means x is equal to 0. 3 minus x squared is equal to 0. So what will make this equal to 0 if x squared is 3? So what would x be then? It'll just be plus or minus the square root of 3. Right? So make sure you know how to get those critical values. So far, these are the possible points of inflection. So what do? The next step is to test for concavity by looking at the change of signs of y double prime. What we'll do is we get our number line and look at all, mark 0, negative square root of 3, and positive square root of 3. So let's do that. Alright, so here we have your number line, and so now the next thing we need to do is get our test points. So remember that square root of 3 is approximately 1.7, so this is negative 1.7. So why don't we use negative 2 as our test point and say negative 1 right here, and then 1 and 2. Okay, so now we plug in negative 2 into the second derivative. So that becomes positive, and 3 minus that becomes 4. So positive times negative, this will be negative here. Alright, so now let's test. So that's one interval. Okay, and then another interval. And so on and so forth. So let's try now between negative square root of 3 and 0. If there is a change of concavity, this becomes a point of inflection. So we plug in negative 1 in here. So let's plug in negative 1. So you plug in 4, negative 4 times negative 1 make it positive. Then 3 minus negative 1 squared, whole thing squared, that becomes positive. So positive times positive is positive. So you see how there is a change of concavity from concave down to concave up, means that this is a point of inflection. Okay, let's see now to the right of 0. So when we plug in the 1 into the second derivative, so that's 4 times 1, that's negative. 3 minus 1 squared, that's positive. So this is negative. The sign of the second derivative in the interval from 0 to square root of 3 is negative. So you have, again, another point of inflection occurring at x equal to 0. And then to the right of square root of 3, we get what? We get that this is, well, let's see. Negative 4 times 2, that's negative. 3 minus, you square 2, you get 4. So you have negative times negative is positive. So again, you have a negative concavity and a concave down to concave up. means that all these critical numbers that we got out of the second derivative, these are all points of inflection. So we found a local extreme values, and then we also found points of inflection. So the question is, are we ready to graph? Well, let's see. I think so, because if we gather all the local minimum and a local max, okay, you get the local minimum, local max, and then you plot those points of inflection, I think we're ready to graph it. And then recall that what we have to expect is that from negative infinity to negative square root of 3, it's concave down. And then from square root of negative square root of 3 up to 0, it's concave up. And then from 0 to square root of 3, it's concave down again. And then from square root of 3 on to plus infinity, it's concave up. Right. So let's see, how do we graph that? And I think the next slide will show us the graph of the function. Right, so you have how many points of inflection? The one at 0, 0, 1. If you plug in 0 here, you'll get 0, 1. And then you have negative square root of 3 and positive square root of 3. These are your points of inflection. And we said that it's concave down to the left of negative square root of 3. See, that's why it's concave down. And then from negative square root of 3 up to 0, it's concave up. And then remember that negative 1, you have a horizontal line tangent to that curve. That's why you have a local minimum. Okay, because it's concave up, so it holds water. And then from 0 up to square root of 3, you have a concave down. And then you test it at x equal to 1. We see that you have a horizontal line tangent to the curve. So that, and then you have a concave down, which gives you the point 1, 2 is a local maximum. And then from square root of 3, right, square root of 3 somewhere here, square root of 3 on to plus infinity, you have a concave up. So we have looked at all the points of inflection. We looked at the local min and local max. Now we look at the big picture. Since this is this function will be asymptotic to the horizontal asymptote y equal to 1, we can conclude therefore that this is an absolute minimum and an absolute maximum occurring right there. Okay, so we have graphed y is equal to this ratio x plus 1 quantity squared over 1 plus x squared.